finish our material on factoring, what we want is to be able to put all the pieces together. The different factoring techniques that we've learned over the past couple of classes, how do they all work with one another, and how do we decide when to use which? So really, primarily, we learned 3 strategies so far, and 2 of them are really the same strategy in disguise. First was factoring out the greatest common factor, GCF factoring. That was the first kind of factoring that we ever did when we started our previous topic. The second was we learned the sum and the product method. Sum and product for trinomials. This is the method where we say we need 2 numbers that add together to give me this and also multiply together to give me that. And this is how we were able to factor a lot of quadratic trinomials, but only at the time quadratic trinomials whose leading coefficient was 1. And so in our last meeting, we developed, let's call it method 2.5, because it's really the same one as method 2, it's just augmented a little bit. That's the AC method. And this is for trinomials whose leading coefficient is not equal to 1. It's actually a generalization of the sum and product method with leading coefficient not equal to 1. And I've written these methods up here on the board in the order in which we usually think about applying them. So the greatest common factor method is almost always the first one that you think about when confronting a new problem. Because if there is a greatest common factor that you can bring out of all of the terms in a polynomial, then doing so will make your problem easier. Right? Once you bring the greatest common factor out, the cofactor that it gets paired with will be a simpler polynomial that then we can use these simpler methods to try and factor as necessary. So if I look, for example, at one of the polynomials up on the screen right now, this looks very much like one that we factored in class on Monday, 3w squared plus 3w minus 90. If the question is to factor that polynomial completely, what's the first thing that you think we ought to do? Ask yourself, what is the greatest common factor between these 3 terms, 3w squared, 3w, and 90? I'm going to make this a little bigger because it's harder to see in the back of the room. 3w squared plus 3w minus 90. If we think about those 3 terms, what is the greatest common factor that I can bring out of all 3 of those terms? What do they all have in common?
3.
They have a 3. Anything more? Any factors of w in common to all 3 of them? No, because we have one term in particular that doesn't have any w's in it at all, and therefore anything which has a w at all is not going to be a factor of that minus 90. So yeah, 3 is the greatest common factor in this expression. So then all we need to do is fill in the missing factors. 3 goes into 3w squared how many times? 3 goes into 3 once, and then the w squared has to be accounted for too. Right? By the way, this looks an awful lot like long division, what we're doing right here, because that's exactly what it is. We're dividing this 3 out of each of the 3 terms inside of my factor lattice here. What's the missing factor between 3 and 3w? 1w. And between 3 and negative 90? Negative 30. So one of the things to try not to mess up along the way is if you do use this lattice method to factor, as I always have done in showing these techniques to you over the last couple of classes, don't forget also to copy it back down in its algebra form. So that what we really did in that factor lattice is factor the 3 out of the quantity w squared plus w minus 30. And now that we've got that 3 factored out, the question is, yes, we've factored, but have we factored completely? Can we factor this trinomial any further, the w squared plus w minus 30? Now that we've exhausted the greatest common factor avenue, because once we bring the greatest common factor out, it's out, right? And we're done with that step in the process. So what's the next consideration? What's the next technique, the next method that I might consider using for this trinomial, w squared plus w minus 30. What would be the next question that you would ask yourself in your mind about that polynomial? The question that we're asking is about a sum and product, right? We're going to be looking for a pair of integers which add together to give me the b coefficient, the coefficient of the first order term here. And in this example, that's the secret 1 that's sitting in front of the w. So the two numbers which solve my sum and product puzzle are going to have to add together to give me 1, but they're also going to have to multiply together to give me how much? Negative 30. Great. So we know we want the product to be negative 30, and we want the sum to be positive 1. So then the question is, what pair of numbers solve that puzzle? 6 and negative 5. Yep, 6 times negative 5 is negative 30. 6 plus negative 5 is equal to 1. So if we're doing this with a lattice, we would use that solution to split the middle term. We would put 6w in one of the squares and minus 5w in the other square. And then we would use that splitting to solve the rest of the puzzle. What's the greatest common factor between w squared and 6w? Well, there's a 6 in one of the terms that's not in the other. But there's a w that belongs to both terms. And there's no number other than 1, which is a common factor of both 1 and 6. So w is the greatest common factor there. And if I then fill in the missing factors here, what's the missing factor between w and w squared? And between w and 6w? Plus 6. And then finally, what's the missing factor between 6 and negative 30? Negative 5. So how then does that mean that we factor w squared plus w minus 30? Awesome. By the way, we just took the long way round the mountain on this sum and product example, because usually, at least when we were first practicing sum and product, we went kind of directly from this to this, right? We usually didn't go through this lattice the way we just did it now. We reserved this fullness of this method for when we did the more general method, the AC method. But this illustration shows that those are really just doing the same thing. When we win the sum and the product game, what we're really learning to do is to split that middle term. In this example, that was the 1w. Split it into a 6w minus a 5w. And in doing so, that lets us then use the rest of this factoring method, which, by the way, if you align this with what we're reading in our textbook or what you might see elsewhere online, this is actually just a repackaging of a method that's called factoring by grouping. And the grouping here, what's meant by the grouping here is that we sort of group together these first two terms, the w squared and the 6w, and I highlighted that first row in the lattice. I'm looking at them first and factoring out their greatest common factor, and then using that to get the rest of the process going. So we're able to factor a group of w plus 6 out of the w, and also a group of w plus 6 out of the minus 5. But there we are at the end of the problem. And so in all of our factoring examples, I'm going to have you get together with one or two other people and work on the other ones that are up here on the screen. But in all of our factoring examples, that's the trajectory that we tend to take. Look for greatest common factor first and take it out. Because A, it's a straightforward thing to do, and B, a lot of times it cuts the problem down to a much simpler one that we're able to solve. If we just looked at this in the beginning because it has a leading coefficient that's not equal to 1, we might think that we would have to go directly for the AC method, which we could have done, but it actually wasn't necessary. Because once we factored out the greatest common factor, we did have a trinomial whose leading coefficient was 1, and we could have just used the standard sum and product, go directly to this answer of w plus 6, w minus 5. So it's only by bringing out GCF first that you'll know whether you're then applying the more complicated methods to the simplest versions of the polynomial that you can.